Okay, so this problem is saying if you roll a die 100 times, what is the approximate probability that you will roll between 10 and 15 ones, inclusive? So what I'm hearing is, what is the probability that we're going to roll between 10 and 15 ones? So now what I'm hearing here is if I either roll a 1 or I don't. So to me, this is implying we are looking at a binomial distribution. So if we're going to approximate the normal to a binomial distribution, we need to give it that little bit of buffer. So what we're going to do is on the low end, we are going to subtract half a value, one half. But now we can't leave it as x anymore because we're giving the buffer, so we have to indicate we've made the change. So then on the upper end, I'm going to also add that half. So there we go. So now that's going to leave us with 9.5 and 15.5. So now we're going to work from there. So now the problem goes just like normal. So the first thing we need to know is what is our expected value, or our mean, and we need to know our standard deviation. So the nice thing about our mean or our expected value, it's easy to calculate in binomial distributions because it is just your number of trials times the probability of success. So in this case, they said we're going to roll a die, not flip a coin. This problem is roll a die 100 times. So all we're going to do, quite simply, is say this is just 100 times what's the probability of success. Well, in this case, we'll define success as rolling a 1, since they're saying they want us to roll between however many ones. So that's 1 out of 6 on a die. So therefore, this is going to be approximately 16.67. Now, for our variance formula, or sorry, not variance, standard deviation. Our standard deviation formula is quite simple. It is n times p times q. Well, we already did part of that. It's 100 times 1/6. Now, p is the probability of success, so therefore q is probability of failure. So if 1/6 is our likelihood of rolling a 1, 5/6 would be our likelihood of not rolling a 1. So we can work this math out very easily, and we get, it's a very long decimal, so we're going to round this one as well, so we'll change that to approximately 3.727. Okay, so now we have everything we need to be able to change our scores here into z-scores. So the probability of our value minus the mean was 16.67 divided by the standard deviation, which was 3.727. So then less than or equal to z, and now the same thing on the other side, which is 15.5 minus 16.67 divided by 3.727. There we go. So now we find our z-score. So there's the rounded z-scores. So now what you need to notice is the values are both negative. So when we're looking at our z-scores on our standard table or z-table, we need to remember that the really low one, we'll call it down here, this is negative 1.92 standard deviations below the mean. The other one is negative 0.31 standard deviations. So they're both going to give us measurements that are compared to the mean. So that one will be to there, this one will be out to there, so we're going to have to subtract the two values. Just remember that. So looking these up on the z-table, the value of, now they obviously don't have the negatives, they only have the positives because it's symmetric, so I'm looking up 1.92, not negative 1.92. So 1.92 has a value of excuse me, I just lost it, 0.4726, and then the other z value, the 0.31, has the value of 0.1217. So therefore, we need to take our red value and subtract our green value. So minus 0.1217, and that will give us we go, 0.3509. So therefore, we know that the probability of this problem is 35.09%. So looking back and really thinking about the answer, what we're going to see here is what we're saying is the probability of having between 10 and 15 ones. So when you roll 100 dice, the probability of having between 10 and 15 is about 35%. Okay, I hope that made sense. Key thing to clue in on here is why did we use this plus and minus of a half? Because it's a binomial distribution, so we are able to do the problem that way. We're able to use these special formulas for expected value or mean, and standard deviation makes the problem much easier. Okay, best of luck.